Hi, welcome back to Spring CS170. Just going to pick up where we were for Chapter 9, the fetch execute cycle. So we're at the machine instructions part. But before I do that, let me get back to here. So you remember there was a link before, which I just posted to my resources here. Right, so here's my resources sections, and you see the week of February 8th. How computers work is this. And this will break down all of the CPU, memory, and whatnot. Goes into more details. Pretty much should be hitting on all of the different things that I was talking about. But you see some bits here that kind of organize it in like a nice little grid here, talking about how fast it is to get to these memory locations, right? And whatnot. So there's a pretty good resource. You want to maybe take a look at this. Um, Let me step back here. So this is instruction pipelining, which we're going to get to in a second. And this might kind of maybe lay it out a little bit more detail. So I'll put this link onto my resources also. So anyway, here we are, machine instructions. Don't know how much you want to get out of this, except just to kind of understand like generally what's happening. And it's kind of just giving an example of what I was talking about before, where you look at the instructions that the CPU is doing, right? You have what is it going to actually do. So in this case, we're talking about doing a multiply. And then what is it going to do it to, which is this and this, right? And this is actually not the numbers themselves, but actually the memory location of those numbers. Okay, so keep that in mind. You're not actually doing a multiply of 2000 times 2080. This would be the memory locations. Okay, so that's more of just a concept to understand. Don't worry about the actual particular number here or whatever, right? Just recognize that this is like the location of whatever data you're going to be multiplying. And then likewise, you know, when you get the results of that, this is another memory location you're going to store the value or the results that came out from this multiplication. So that's really the main thing you want to take out from this, right? And then you can see the notes down here a little bit, right? But this main takeaway up here, okay? This particular series of pages on the PowerPoint has a number of notes on here, so I will make sure to save this into my resources with the notes also, okay? So computer clock, you can imagine there's like a whole bunch of moving parts um, on the computer, right? So just like in everyday life, um, you know, we have a whole bunch of people moving around. We're all doing different things, right? Maybe we're meeting for class, maybe we're going to work, or we're having a meeting to do something. So there's all these different pieces or people moving around and interacting with each other. And so how do we make sure that we synchronize or coordinate these activities? Um, so there's the idea of a clock, right? Time, right? Uh, so by the same token, you have a computer clock that works kind of in a similar way, where everything within the machine is working off of this clock cycle, right? And with the speed of computers, you can imagine like these clock cycles are getting bigger over time, right? At one point, megahertz was pretty fast, but now you're really getting into like gigahertz, right? So this is like how many ticking of the clock is happening per second. Okay, so megahertz and gigahertz, right? Um, and you have some more notes on that down here, which I'm not going to read through. You can kind of read that on your own. Okay, so here's one particular idea or concept which you probably want to pay attention to and make a note of that, which is why I also took a separate link of on the Wikipedia for instruction pipelining, again, to kind of try to explain this a little bit. Okay, so I'm not really sure how clear this would make sense to you, but I'm gonna try to see if I can explain this picture to you a bit. Okay, so um, just imagine like, remember we were talking about like the steps you're doing, right? You have like within the CPU, you're gonna have like the fetch, you're gonna have a decode, you're gonna have to execute, and you're gonna have to store, right? So like just remember back here, right? You got this, you do this multiplication, then you're gonna store it out to this memory location, okay? So just think of it essentially as 4 distinct steps to do something, right? So each of these clock ticks matches up to one of these, okay? So uh, if you count, there's 4 steps here, so you would be talking about 4 clock ticks, okay? And so what does that kind of mean? Um, so if you just kind of think of it simplistically, you could kind of say, well, okay, you know, I have my CPU and there's like these 4 things that it has to do. I'm going to get something to do, and it's going to take me 4 clock ticks to do it, and I'll get done, right? So 1, 2, 3, 4, right? 1, 2, 3, 4. That's this instruction 1 here, let's say, right? Then I'll say, oh, now I'm done with this. Let me go and get another one, get another instruction to work on. Okay, that's one way to do it. But if you look at it from like the resources from the computer standpoint, it's probably not the most optimal because, you know, the part of uh, the cycle that you did for fetching is idle while it's working on decode, right? And then likewise, after you get done with the decode and you do the execute, the fetch and the decode are idle, right? There's an opportunity to do some extra work here, or do these steps for another instruction while you're working on it, right? And likewise, if you do the store, while you're doing the store, if you don't do a fetch, decode, or execute on some other instruction, they're kind of sitting idle. They're kind of wasted resources or whatnot, right? And so that's where this idea of pipelining comes in. Okay, so this is where I'm not really sure this explains it clearly. I kind of like this explanation a little, or this visual a little bit better. But you know, you can take a look at it and you tell me what you think, which one is better. But essentially, you can see here's the first instruction, and instead of waiting for instruction uh, 1 to complete all the way through and then starting instruction 2, you can see actually it's like 1 step behind, right? It actually works through such that by the time we get to like this 4th clock tick here, where basically instruction 1 has completed, instead of like going back to like the first part, the first step essentially to work on instruction 2 has already, it's like trailing right behind it. It's already done 3 steps out of the 4 steps here, right? And likewise, instruction 3 has already done 2 steps behind instruction 1, right? And then likewise, instruction 4 is doing 1, right? So instead of doing it in a serial fashion, you're basically stuffing more instructions in over the same period of time. In this case, we're talking about 4 clock ticks here, right? So when you, in the time that you've done 1 processing cycle for instruction 1, you have these other instructions 2, 3, and 4 right behind it, filling up those slots, right? So you think of each of these slots like fetch, decode, execute, and store as separate buckets, right? Once you empty out from one bucket and goes to the next bucket, now you have an empty bucket. You can do something with it, and you know, the idea of pipelining is to utilize that bucket by doing the next instruction. Okay, hopefully that's the most simple and clearest way I can try to explain what we mean by pipelining. Okay, but take a look at this, right? This maybe explains it more eloquently than I do, right? And see if you can understand what the pipelining means. Now, you know, obviously this is like the way this is drawn up. This is an ideal world, right? there may not be a chance for you to actually execute in this fashion all the time in an ideal way, right? So when might we have a problem? An example of a problem might be like, well, I actually can't do anything for instruction 2 until I get the output from instruction 1, right? So if instruction 1 and instruction 2, let's say, are two totally different operations on acting on two different pieces of data, that's fine. That's great, actually. That's the perfect scenario. But if you're actually waiting for, let's say I'm adding 1 plus 1, right? And then I actually need the result of that to feed into my next instruction, which is to take that result and multiply it by 3. Um, you're not going to be able to do that because you're still waiting for the output from instruction 1 before you can do anything. So that's a typical situation where this is not really going to be ideal, but you have to look at, it depends on what type of work you're doing, but probably there's a decent amount of times where you do have an opportunity to do some pipelining because the operations and the data going with this independent of the preceding instruction. Okay, so that's the idea of pipelining. Hopefully you get the idea and take a look at it. Like I said, just think of it this way. I did these 4 steps here, 1, 2, 3, 4, right? And then because I did this while I'm on the 4th step, these first 3 buckets are empty and they could be utilized. In this case, we utilized them to do instruction 2, right? And so on and so forth all the way down. So we ultimately are working on 4 different instructions within this 4 clock ticks, okay? All right, so this one, same thing, talking about how the computers work. And here's the link again. So if you look at it, you say, how do you compare or draw an analogy between um, uh, what you know in real life with a computer, okay? So we have it here in the notes here, right? So if you think about like your refrigerator, the analogy for that from a computer standpoint would be like your secondary storage, right? You can store, quote unquote, a lot of stuff in the refrigerator, right? But it takes you some time. You have to go from your counter, or your work area is your counter area, right, to the refrigerator, get stuff, and then bring it back. And you may not be able to do it in one trip. You may have to do a couple trips to the refrigerator to get stuff. So that's analogous to you storing to your secondary storage, right? And then so on. Like you go to the counter, you place all of your stuff on there for your cutting board, right? And that's your local workspace, your local memory, right? And then you can act on it, right? In this case, let's say you're cutting up the vegetables or something like that. So the act of you cutting it, that's the calculation. That's like your ALU, okay? Um, so take a look at this and see if you can make sure that you can match up these analogies. It's just meant for you to understand a bit more of how the computer, the different components of the computer match up to what you're used to in everyday life. Okay, and like I said, I'm going to print out like this PowerPoint with the notes at the bottom so you can try to understand this for yourself when you study this, okay? Okay. Uh, this is memory, RAM, random access memory. Um, it's basically fairly quick access. It's not the same thing as the registers, which is the fastest access, but obviously it's much more memory than what you can store in your registers. And so your computer would like to access stuff from your RAM to do its processing, as opposed to this, your hard drive, your external memory here. Okay, these are your inputs and outputs over here. Right, you probably are pretty familiar with these things, right? And this kind of refers a little bit to like what we were talking about before when you're looking at memory location, right? So this basically just talks about um, your reference to your memory location and the actual values that you are storing in there. Okay. Yeah, and I think all of this is basically saying is that um, it's not like um, your CPU is doing all kinds of like very complex operations or math. It's actually being broken down into very simple operations, generally like adding or subtracting numbers, right? Binary numbers, right? It's generally at that level that you're doing it, as opposed to like some of the more complex operations that you might envision. Um, there's a process to break all those things up into very small, simple operations, and then it's just going to process a whole bunch of them, right? The scale, like you saw before, you're talking about gigahertz, right? So that's how many clock ticks are going. So it's like a lot of instructions that is processing per second. So the fact that it breaks up something into like 100 different instructions, 1,000 different instructions, 10,000 instructions, is kind of okay, right? And in that way, it reduces um, the number of different types of instructions that you have to do, right? So ideally, you get simple operations, you don't have that many different instructions to worry about, and then you can just like keep on cranking it through. It makes things a lot more complex if you do things in fewer steps, but have a whole bunch of different complex operations that it has to do. Um, it makes the design and implementation of the CPU much more difficult if you did it that way. So the strategy is to go for doing less types of instructions, but do them very fast, right? So less instructions, do them simple, but do them very fast, and the results build on top of each other. So that's the general idea here, okay? And it kind of refers, everything that I just said kind of refers to here in the notes here, okay? All right, so software layers, I commonly refer to it as the software stack, right? But you call it software layers. And you remember what I was saying before, where like below the operating system, you have the hardware, right? And then so everything else on top of that is various layers of software, okay? So the operating system is the common things that you use to interface with the hardware, right? So how do I get the data out of the memory or the hard drive, or how do I display stuff on a monitor, or how do I send stuff to the printer or whatever, right? All the hardware stuff. So this is the software that kind of controls that. So that way it avoids you as a user having to deal with such low level stuff, which you don't care, right? All you care is that you have some information that's displayed on the screen to you, right? So then you work your way up, because again, probably a lot of people don't want to be working at the operating system level either, right? Uh, so then you start to build up these different layers here, all the way up to the point where you get more usable stuff that people care about. Maybe let's say we're gonna talk about like how to display things on the screen, um, and you don't want to actually have to be able to specify that every single time. You just want to be able to have a component to say, okay, when I do this, it knows to display my screen this way, right? Um, in some ways, it's almost like when I look at the HTML, it's very convenient that no matter which web browser I use, I'm able to specify that this is a table. I want a table with this many columns with some sort of border, and then the computer magically generates that for you, right? So that's at the level that typically we want to be at, right? These other layers are more for like hardcore developers who's working on, making things go faster or making things look slicker or whatever. Uh, when I say things, I mean the components that, like a user would use. Um, so it just gets higher and higher to the point where people that are actually making stuff for business benefit, for benefit for you, it's going to be at this top level here, right? Very few times you're going to see someone who is like, let's say, working on the Excel spreadsheet or working on like a web page or something like that, is going to care much about these layers down here. Okay, so um, that's the general idea. These layers are building on top of each other, and it's levels of abstraction and making things a lot easier for the other people who are the more general users of computers. Okay. All right, so let's see what are the different things that we talked about here for chapter 9. Again, these are learning objectives. You should make sure you understand these. So we talked about, uh, you know, the layered software. We talked about the fetch execute cycle. We talked about the different types of memory. Uh, you know, 3 types, right? So you have like on board the CPU, you have the RAM, and then you have like the, I guess, remote storage, okay? Uh, then you have the CPU, then you have, or control unit, I should say. So this is like, actually running the program, right? And then the ALU, the arithmetic logic unit, this is the one that's actually doing the number crunching, right? Uh, you have your input and output, right? Program counter that keeps track of where you are in the program. So this wasn't on the PowerPoint, but you have this idea of branch and jump instructions, right? And I don't know if you kind of intuitively think about it, what would that mean, right? If I say something is going to branch, right? So here's my programming going straight ahead, and then maybe when I hit certain criteria, I'm going to branch off and do something else, right? So um, maybe if I come up with a calculation where the number is greater than 10, I should go to the right. And if the number is less than 10, I go to the left, right? Um, it doesn't literally do that, right? I'm just trying to draw like a picture for you, okay? And the same thing is like from a jump perspective, right? I'm moving along and I didn't hit a certain criteria, or I did hit a certain criteria, and say, oh, when I hit this criteria, I don't need to do these next 10 instructions, right? And I'm gonna go somewhere else, right? So that's the idea with branching and jumping when you're doing your code, okay? Um, you know, interpreting the instructions. So you remember that multiply example I showed you, the computer clock. Uh, we were talking about the megahertz, gigahertz, uh, the pipeline. Uh, Pipeline's not on here, but pipeline definitely you should know, right? But pipeline relates to these things here, right? So we talked about, why do we have a computer clock? Why do we have such thing as a clock tick? Is really to sync or coordinate the activities across the computer, right? And then the pipeline, which is not listed on here, which I should just add it on here before I save it, which I will. Um, make sure you understand that too, right? And how, based on the clock ticks and each of those steps on the fetch execute cycle, you're able to maximize your performance, okay? And what the limitation may be in terms of dependencies between the instructions, okay? So that's it for chapter 9. If you can, go ahead and, take a look at it. Let me know if there's any questions. Other than that, we're good for this week. Thank you.